So welcome everybody to the landscape of Saclay. Very flat, but then there's a valley. So we'll see. We're very happy to have you here. Thank you for coming. It's so nice to have this crowd. And I'm sure we have a very nice conference. Well, I want to start, thank the young organizers, Nico and Alvaro, who did a lot of work. Just one thing, for the Wi-Fi, I'm not sure you can read. If you have everyone, go for everyone. The second option is to go to this ON enregistrement and put Alvaro's email as contact. You're visiting Alvaro, everybody's visiting Alvaro. Then he needs to validate, and then you can go to the second ON access with the password that it will give you. But hopefully everybody has it wrong. You don't have to do that. It's easy, it just takes 2 steps. Okay, so we can start. Very happy to have Thomas as the first speaker. He's less happy to be the first speaker. So, review on Moduli stabilization, scale separation, and holography.
Thank you, Mariana. I must say, it's always a pleasure to be back in a place where I was here for my postdoc, and I have very good memories of this place. So I've been asked to give a review talk, and that means I talk mostly about things that I haven't done myself. And so a lot of the questions I will not be able to answer, but luckily all the authors of all the papers I discuss are here, and so questions will be bounced back into the audience, okay? So this is a topic, what I will be talking about. And I'm going to start with a disclaimer, which is that this is a lot that was asked from me. And I thought it's better to give a little bit of a focused presentation. So unfortunately, that means that there's too little attention to things like the large volume scenario, KKLT, M-theory on G2, heterotic model building, and so on. It's partially covered only by the research talks later. But I mean, I do say some things, okay? So people are always welcome to comment more, especially during the discussion sessions. There's no de Sitter in this talk. And there's an overview talk by Severin, or there's a review online. Okay. So I'll start with the motivation. And then when I say it's focused, it means that I decided to talk mainly about type 2A flux vacuum. Why? Because moduli stabilization and scale separation are particularly simple and clear in that case. Then I'll discuss the link with holography, and if time permitted, I will end with some statements about the swampland. Okay? So let us start with the motivation. So string phenomenology in the conventional way, it means we want small extra dimensions, and we want stabilization of the moduli related to these extra dimensions. So even if it's non-geometrical, there's extra stuff out there, which we need to stabilize. We should not be able to see it in any obvious way in our 4-dimensional world. And so the question is, can we get these features? If so, how small can these extra dimensions be, and how stabilized can they become? String phenomenology is an old topic. People would have said this is for sure okay. The swampland challenges this a bit, and I think it would be interesting to ask yourself how small, how stabilized. And so to get maximal computational control over this question, we can study this in ADS. And the nice thing about studying this in ADS is that we have holography at our disposal. But then the weird state of affairs in our field is that when you look at the vanilla top-down models, and by vanilla I mean actually understood top-down ADS-CFT pairs, they seem to be like this: ADS-Z cross XN, where X is some compact manifold, which has the same size as the ADS space. All right? So that's not really what we mean by small extra dimensions. And so the CFT question you could ask, I mean, first of all, it's a geometrical question. You could say, can we make X as small as we want in ADS units? And if so, what would be the dual CFT description of that? I think the better way of phrasing it, which was, I think, done in a paper by Polchinski Silverstein and later by Eric here, the proper way of thinking about this question is, if you are given a CFT, how many bulk dimensions does it predict? That's the proper statement. Okay, that's the question we're interested in. Is it 10, 11, or less? This should be a number that you can compute. Okay, this was about scale separation. What about moduli stabilization? So, problem of moduli stabilization means that we do not want two light fields, right? Because clearly moduli spaces do not or are not expected to exist at all when supersymmetry is broken. So the proper statement is you do not want two light fields, because clearly that's a clash with phenomenology, with observations, unless extremely light fields for some reason don't couple to the observable sector, and that's what we call a dark sector. Okay? So either you make a dark sector, which is very light, or you say moduli should be sufficiently heavy. Okay? That's the phenomenological problem. That's not a holography problem. But as I said, when supersymmetry is broken, one cannot expect massless fields. And the generic expectation, perhaps, from naturalness or whatever, is that moduli fields should be around masses around the SUSY breaking scale. So why do we worry? You could ask yourself this question: why should I care? Well, as people who are interested in UV completion, I personally think of this as a computational problem. We would like to understand the vacua we live in computationally so we can study them, right? And so this really comes back to the Dine-Seiberg problem, that, okay, there are no moduli once supersymmetry is broken, but then what you typically expect is that quantum corrections to some effective potential, they are important, that strong coupling, so that's where you expect to be stabilized, but then we cannot do computations. So that's what I mean by saying that the problem of moduli stabilization to string theorists is a problem of computational control, especially when supersymmetry is broken. So, but then let me not break supersymmetry. So let me use the words before the uplift. And then we have an ADS vacuum. And then moduli stabilization. Some ADS vacua can have moduli, true moduli. But so if that is absent, it means you have an isolated CFT. It's a CFT without a conformal manifold, as we say, okay? And also this isolated CFT should have a very sparse spectrum of low-lying single trace operators. These are bizarre CFTs. I will discuss more about why they're bizarre, and these are two original papers on this question. All right? Now, let me get back to the definition of scale separation. What do we mean with small enough? We said extra dimensions should be small enough. Yeah. Very good. I don't have a strong opinion on this, but I would say the following statement. If I have string theory, I have an ADS vacuum which is supersymmetric, which is weakly coupled, meaning that the bulk description is essentially GR. I expect there to be for sure a CFT in the holographic regime. All right, so when I would, for instance, discuss large volume scenario, I start from a non-supersymmetric ADS, then I don't have a strong opinion. I know there are strong opinions on whether or not they should have a CFT dual. I don't know. Yeah. Even if, I would say it always secretly as a CFT dual. Okay, now I'm actually giving my opinion. And it goes as this. If an ADS vacuum is non-supersymmetric, say it's metastable, it will decay eventually to another ADS, which is supersymmetric. So that original ADS should be some kind of a state in the real supersymmetric ADS. So you should be able to produce it locally. So it should correspond. There's a more fundamental SUSY CFT description of this. Yep. All right, what does it mean to have small enough extra dimensions? So the proper way of thinking about this is that you could say whenever I have a compactification, I for sure have two length scales. There's a Kaluza-Klein length scale, which it's probably not entirely correct, but for this whole talk, I'm just going to assume it's related to the volume, which is of course not sufficiently precise. because what we call the Kaluza-Klein spectrum must be related to eigenvalues of quadratic operators, which are way more complicated than the Laplacian on the compact space. It's very difficult to discuss this in general, so I'm just going to take as a proxy that the Kaluza-Klein scale is set by the overall volume of the internal space. Then, as I said, we're going to study ADS compactifications. Then I have, okay, I'm a true cosmologist here. I call it Hubble scale. Other people would say the ADS scale. Okay, so I have these two scales. And what I want is that the ADS space is significantly larger than the internal space, right? So in terms of mass scales, I would have that the mass scale associated to the cosmological constant is much, much smaller than the Kaluza-Klein mass scale. Somehow the symbol got turned into a small m here, but you know what I'm talking about. And the problem is that when you open a book on quantum field theory on naturalness, the cosmological constant problem, they're telling you that what we expect is that the ratios of these two scales is order 1. Because what's the usual definition of the cosmological constant problem, or a version of it, is that the mass scale associated to vacuum energy should be of the order of the cutoff scale. The Kaluza-Klein scale is a cutoff scale. So you expect these two numbers to be order 1. So from the point of view of a string theorist or somebody working on extra dimensions, this is interesting, right? So the failure of a solution to look 4D, this is what it means. This is the failure to look 4D, is the same as not having a cosmological hierarchy, right? But here is the weird thing. I'm only allowed to open a quantum field theory book and study those principles on the condition I'm allowed to use 4D quantum field theory. But 4D quantum field theory is only possible when this is going to 0. So there's a danger of circular reasoning here. So the proper way to address the cosmological constant problem is always in a 10-dimensional UV complete setting. Okay? So what am I trying to say is that the cosmological constant problem is deeply related to the problem of scale separation. So can we have scale separation, yes or no? Or is this thing that we knew from EFT, is it always true, like in the vanilla ADS-CFT pairs? You see, there are no-goes, probably less important, more important than actual conjectures, but both of them exist against scale separation, at least on the gravity side of the problem. So let me, Yes, excellent question. So I might be wrong here. I do not know of a Minkowski compactification, of a Minkowski solution which is not 11D without moduli. Yeah, so yes, true. So if it's absolutely true that this definition doesn't exist for Minkowski solutions. And you can always, take type 2 on a Calabi-Yau. We do not, so you have n equal 2, you expect things to actually exist, these solutions to actually be there. Quantum corrections don't destroy them, but then I can make them as scale separated as I want. But it's meaningless because it's with a moduli space. So by a very small amount of energy, I can just upset this hierarchy, right? So phenomenologically, I would not find this interesting, an interesting form of scale separation. So I'm still in the motivation section. This is going small, but slow, but it captures the essence, I think. So what I want to do is I want to show you at least a taste of these no-go theorems on the gravity side. You might not be interested because as with like the Malacena-Nunez no-go theorem, you say, of course I go around it immediately. Yet I believe these no-go theorems are important to understand why it can be difficult to get scale separation. So here is a trivial calculation, try to follow it, okay? So we're doing 11-dimensional supergravity on a compact, smooth manifold, no singularities, no branes whatsoever, okay? This is a trace of the Einstein equations over the 4 dimensions. So R4 is a 4-dimensional Ricci scalar, and then I can derive it's always given in this form. I work in a formalism, in a democratic formalism where all fluxes are internal, okay? So all the squares here are with Euclidean metric, Euclidean signature. So I see that indeed, this is strictly negative, that's Malacena-Nunez. I can only have ADS. What I see is that the internal space is strictly positively curved. There's also a name for this one. And now what I'm going to do is I'm going to take the ratios of these two numbers, okay? And I'm going to integrate those ratios over the internal space so that I genuinely have something that's independent of the position on the internal space. So I take those integrals, and I get that the ratio of those two integrals is smaller than 5/4. I can easily derive this from this expression. What does that mean? Okay? It means that if I define the curvature radius in the following way for any compact manifold of dimension d or non-compact manifold, this is a definition of curvature radius. Okay, then I find that I cannot take the curvature radius of ADS to be arbitrarily large with respect to the curvature radius of the internal space. I cannot decouple the two. That's what the previous inequality tells me. All right? So for ADS side, this defines the ADS length, and for the other guy, this is what you define usually as the Kaluza-Klein scale. But there's a big if, okay? So there is the curvature scale and there's LKK, and I'm saying what if they're of the same order? This is an important what, it will come back. Then this inequality shows you immediately a no-go for scale separation in 11 dimensions, given the assumptions I explained. All right, so keep in mind, this works in this number. The curvature radius is related to the Kaluza-Klein radius. So in this case, you actually arrive, these kind of calculations show you that there's an extension of the Maldacena-Nunez no-go theorem. So Maldacena-Nunez, under the same assumptions that I laid out, excludes the Sitter and Minkowski with fluxes. What we're saying, we also exclude ADS with a tiny cosmological constant, so the scale separated ones. Okay, these kind of reasonings, but much more precise, is laid out here, where there's a lot of the mathematical technology to properly discuss this mathematical question. I invite you to look at this paper, okay? Yeah. So what are the ways around? This is identical to Maldacena-Nunez. So an obvious way around is to use orientifold. D-branes don't work. You can say they're sort of singularities, but they don't work. You can show that. And then indeed, type 2A flux vacua were found to allow for arbitrary scale separation. Then there's a problem here. Yeah. Orientifolds plus quantum corrections. So I'm just adding stuff on it. And this is really the type 2B landscape. This is how I think about it. So you start with the no scale vacua of GKP. And then you add quantum corrections to stabilize the moduli. And the reason they're moduli, they're scale separated as well is a little bit because you evade the no-go theorem. Then, what has been done recently, Bruno is here in the audience, these simple solutions with Casimir energies. They're remarkably simple, at least the ADS ones, and they allow arbitrary scale separation. But they're not like studied in so much detail yet. Then, the final option that I know is to just use fluxes. Fluxes alone, Freund-Rubin vacua. You could say, hey, wait a minute, you just excluded that. No. I excluded that on the condition that I cannot decouple the curvature radius from the Kaluza-Klein radius in the right direction. Okay, there are mathematical conjectures that this is impossible, but this is an unsolved problem. I will come back to it later. So this is an excellent mathematics problem which has not been solved. There's only a conjecture now by Vafa, Yao, that this cannot happen. There's no actual proof. This is, I think, super interesting. I discussed with some mathematicians, and people literally find it interesting, but they cannot show anything in any direction properly. And the things that I'm clearly skipping is M theory with quantum corrections, derivative corrections, and so on. There are also some works on heterotic model building. Yeah. No, it's not even required. I can have a more general solution than Einstein. Absolutely, agreed. Yeah. No, no. The counterexamples are negatively curved spaces. No. Look at what I did in my previous slide. I showed you that within the assumptions made, the internal curvature has to be positive. The only way a compactification can sustain internal negative curvature is if there's an orientifold plane. Without orientifold planes, it's impossible. But the orientifold planes immediately allow me to circumvent. Right? So it is, of course, Riemann spaces are examples where I decouple the two ratio. Right? So, but there's not a single known positively curved manifold that can do it. This is really remarkable. So the rest of this talk is, a lot of it is devoted to this, okay? Then I want to add one more thing. I'm going way too slow, so unfortunately the swampland stuff will have to go. Some people will be happy. Why are the works on moduli stabilization, why do these works tend to be scale separated? It's a question that's not sufficiently asked, okay? So if I go back to the pre-swampland string phenomenology literature, KKLT large volume scenario, you will see that those solutions are scale separated, but not parametrically, yet they are. And the reason is the following, that if these solutions would not be scale separated, they would not be consistent. Okay, so scale separation had to be built in KKLT, in large volume, because these solutions are constructed in a hybrid top-down, bottom-up point of view. So without scale separation, you would not have been allowed to use the bottom-up point of view. You would not have been allowed to use 4D effective field theory. Okay, so there's a good reason why LVS and KKLT tend to come with scale separation, because they use n=1 effective field theory in the end, okay? And the reason they're hybrid is the reason why we have this conference. If these would not be hybrid constructions, they would be fully string theory, there would be no discussion. The calculations have been done and over and out, okay? There would not be no discussion. All right. So for the classical solutions, so fluxes and orientifolds, and also the Casimir supported ones, scale separation can be actually made arbitrarily large, which is not the case for KKLT in large volume. And so there's an infinite landscape because of an unbounded flux quantum n, right? And as I said, type 2b has bounded fluxes, and scale separation is yet claimed to be exponentially strong. And especially in the recent years, there have been advances by the Cornell group. Maybe Jakob will talk about it, I don't know, we'll see. All right, now let's go to ADS scale separation on the classical side. I mean, this was suggested by Eric, not me. So, and recently, this is interesting, there has been a review on this topic, okay? So please check that paper if you want to know more. Everything can be found in this paper. Okay, so here is a quick and dirty way to see, like in a few lines of computation, why type 2a flux vacua can have scale separation. So the way we do it is we're writing down a metric in 10D string frame in the following way. So this is a d-dimensional non-compact space. This is 10 minus d compact. This metric has unit volume, so all of the volume sits in this scalar row. What is this tau here? So tau 0 is the vacuum expectation value of tau. So that in the vacuum there's just a 1 here, what you expect. And this tau is defined in the following way. It's like the volume to some power, there's a string coupling, and it's the usual thing that you do to go to Einstein framing 4D. So if you dimension reduce, the d-dimensional action will look like this. There's this tau 0, this vacuum expectation value to some power. There's the Ricci tensor in d dimensions. And here there's some scalar potential. And it's multiplied with t0 to the power d. So you recognize that this t0 here is nothing but the Planck mass. It's a definition of Planck mass. Okay? So this vacuum expectation value is indeed what you know as Planck mass in string units. All right. As I said, to estimate a KK scale, we simply take this approximation. And to estimate a KK scale, I just look at the Einstein equations. So I'm writing them down. Here they are, in a vacuum. Einstein equations in a vacuum. So this is a vacuum expectation value. And then I read off that the ADS scale is given by this combination. So now, it's easy. Scale separation means that I look at this ratio. And this ratio, in this language, is given by rho 0 tau 0 squared times v. And now I need to know whether I can take this thing to 0. So let us check. Okay? Let us check when this is possible. So you see, I can check this as a necessary condition by just knowing the volume and dilaton dependence in the scalar potential. So using string tree level compactifications, I know that one contribution to the scalar potential, which I call VR, comes from the curvature of the internal dimension. So this guy is obviously absent on a Calabi-Yau, but I wrote it anyways. The three-form Neveu-Schwarz flux scales like this with rho and tau. All of the Ramon-Ramon fluxes of rank n scale in this particular way. And if I do sources, dp, op, where p is some integer, it's this dependence. So I'm just saying the obvious thing is that the classical ingredients scale in a way with volume and dilaton, which we all know. All right? And what I'm going to do now is I'm going to try to see whether the on-shell result, wow, there's a problem here. Yeah, whether I can make this small. Okay? So let's see. What I'm going to do now is I'm going to take type 2A on a Ricci flat background, so this guy goes. I'm going to put O6 plane, so I have P equals 6 here, F4, H3, and F0 flux. That means that my potential looks like this. And of course, there are gazillions of scalar fields, which I'm not writing, but that's fine. I'm doing necessary conditions. So I compute this equation, which has to be true in a vacuum, this equation, and I get these conditions. Okay, then I combine them. I mean, this is child play, right? But I want you to understand how powerful it is. So this is a scalar potential. I put in these relations, and I find it goes like -4/9 V4. This means there are only ADS vacua, despite going around Maldacena-Nunez, but that's not strange. You need to do a little bit more work to get the sitter, okay? So we know if they're vacua, they're going to be ADS. So will they be scale separated? Let's see. The only flux, if you be careful about it, you write down your tadpoles. The only flux you know that's unbounded will be F4. So what we're going to do, that's the only thing we can play with. We're going to send the F4 flux to infinity. Okay, let me call that flux quantum n, and I'm going to send it to infinity. So the only way all the terms in the potential can ever balance against this infinity is if rho and tau are going to scale with n in some way. I call that way A and B. So I plug all of that in the potential, and I get these 4 terms which scale in certain ways with A and B. So the only way I can ever get a solution is if they all scale in the same way with A and B. Otherwise, I can never find a balance in that scalar potential, right? I mean, this, yeah. Yeah, this means the Planck mass is scaling. I'll show it, yeah. All right, but there are 4 terms. Here is the magic. If we take B equal 1/2 and A equal 3/2, all of these components scale in the same way. So that's remarkable because I have 4 terms that didn't have to be. And if you fill that in, you will see that V goes like n to the -9/2, so it goes to 0. That's good. Cosmological constant becomes arbitrarily small. I can now compute this number, and I find it goes like 1/n, it goes to 0. So I can get scale separation. This is the magic. Then I want to make sure I'm in supergravity. I check the volume, the dilaton scaling. Okay, the dilaton becomes 0, goes to 0, great. I mean, e to the string coupling goes to 0. The internal volume goes to infinity, so it's in supergravity regime. But the internal volume goes to infinity slower than the ADS range goes to infinity. That's why I have scale separation. So this was quick and dirty, but this is how you predict vacua with scale separation. So now you want to make sure there is actually a solution. Right, so what you do, you're actually going to compute whether there's a solution. But this is how you predict solutions to exist. This is how you play the game. So what you do is the usual way. You apply the formalism of Grimm and Louis, which are the formulas for n equal 1 Calabi-Yaus in type 2A with fluxes. And here I want to have in memory Kostas Kounas, who unfortunately passed away. And he was very passionately complaining about Calabi-Yau with fluxes not being Calabi-Yau. And his complaint, which maybe if you're old enough you remember from a conference in Greece in 2005 or 4, actually this complaint of his has become sort of a constant in this topic. Okay, in that sense he was very visionary. So what you do, it's the usual game, right? I guess most people here know this. You define a complexified Kähler form. Here is a Kähler potential for the Kähler moduli. There's a superpotential that you can write for the Kähler moduli. This is F6 flux, F6, F4, F2, and Romans mass, all right? Then you do the same in the complex structure sector. There's a complexified holomorphic 3 form. There's a Kähler potential for those complex structure moduli, and here is the superpotential. You plug it into your favorite n=1 formulas, and you calculate. And indeed, you get exactly what I showed you on the previous slides with this silly game. You just reproduce it. Even more, you get that with the right kind of Calabi-Yau, you can stabilize all the moduli in this way. All right? Okay. We should do better. Can we write down 10D solutions? Yes. Using this formalism developed here in Saclay with Thomas Yellow and others, using the pure spinner approach, they look remarkably simple. Here it is in 10D for any Calabi-Yau. I got the Romans mass. Okay, there's some parameter m, which is not exactly the Romans mass. It's just a number, an integration constant of the pure spinner equations. This is the F4 flux. You see, it looks ridiculously simple. It's completely generic. This is the H field. It's a real part of the holomorphic 3 form. And I will explain what this guy is. Just give me some time. So this is a solution, and this is the Cosmos constant. Okay, it's given in terms of this little m, which is Romans mass times inverse string coupling, so this guy goes to 0. Okay? If you want to actually, I mean, this is true for any Calabi-Yau. If you want to see how it works for a concrete example, I don't know, just take a 6 torus, orientifold it, orbifold it, and then you just have your 6 Cartesian coordinates on a torus. I just want to show you that, you know, I can make it extremely explicit. Like, this is a full solution, all right? Okay? Of course, I don't show the moduli because I fixed them. But at least you see that there's no catch. There's a full 10D solution. Of course, there is a catch. What is the catch? The catch is in the symbol I didn't explain. What is this symbol? It's the thing in the pure spinner equations that needs to solve the Bianchi identity. Okay? So you see, this is the orientifold source. What's the problem? It's not a delta function. It should be a distribution. It's a smooth form. So we smeared the orientifolds. Okay? This is a complaint of Costas Kounas. The reason we have Calabi-Yau, and it's possible, is because we smeared the orientifolds. So the back reaction of the fluxes, which is positive everywhere, you think there's no way I can ever have a Calabi-Yau with fluxes because it's going to back react. Well, the negative tension of the orientifolds locally at every point cancels that back reaction, so I have a Calabi-Yau geometry. All right, and so this back reaction is not well understood, and it's contrived, so this is not yet a real deal. How did we get here, you know? How come we started smearing? I personally, I don't think, this is my opinion, but it's probably not so relevant, I don't see any problem with this approach whatsoever. And the reason is the following. Whenever, I mean, think of smearing, you take a delta function, you Fourier expand it. Smearing is just the usual statement that you keep the 0 Fourier mode. Right? I mean, we always do this. I don't understand the complaint. And if you keep the 0 at Fourier mode, there's a one-to-one relation between the effective field theory and 10D solutions. It's like a consistent truncation. And so you can ask yourself, is this smearing bad? Well, as I just said, since when is coarse graining evil? I mean, this is standard Wilsonian effective field theory. We all coarse grain. So if you take, for instance, the type 2B landscape, the back reaction in that case of the orientifold or 307 actually can be computed. It's what we do in F theory. And if you check what it means for the effective field theory, okay, it means that you have to dress things with warping, but it doesn't change essentially anything, okay? For instance, it doesn't even affect the position of the complex structure moduli. They're not altered at all, no matter how big the warping is, right? And this is not just true in type 2B. You can also find type 2A examples, which are very simple, where there's F0 flux and O6 planes. And so you can explicitly show something similar to Holt. Unlike complaints of, say, Savdeep Sethi and others, there's no worry about the large volume limit, weak coupling limit, and so on, all right? But this, I must say, you can explicitly compute for non-intersecting O planes. Unfortunately, if you look at, note the analogy of this question, of this discussion, with the attempts to understand KKLT ADS in 10 dimensions, which I think half of the audience here has worked on, it's the same question in my opinion. It's about the backcorrection of the gauge Gino condensate in 10D. Should I worry or should I not worry? All right. Yeah. Yeah. Yeah, that is true. Yeah. No, but this meaning means that I'm ignorant about how the localized solution looks like, but I don't need to know it. I only need to know that it's there. Once I know it's there, its effect in the 4D effective field theory will be what you get from integrating the 10D equations, which is a smearing procedure. But okay, who knows? I mean, this is just my opinion. You could be right. I know people are, for instance, worried that if they intersect, there's light matter on the intersections and we miss those modes. This is another complaint I've heard. And indeed, yeah. Indeed, on a Calabi-Yau, there's no such thing as a consistent truncation. I know what you're saying. Yeah, good point. Thank you. But the vacuum is a consistent solution within that. Yeah, you know what I mean. Good. So if you look at a typical example on tori, the orientifold planes in type 2A are oriented like this. So it's complicated. It's a nightmare to compute the backcorrection. But there was a recent paper by Junghans who emphasized that actually you don't need to think about them as intersecting. They actually, on certain toroidal orbifolds, they do not intersect, but they do point in all directions. So the backcorrection will be a nightmare. Okay? It's not because they do not intersect that you can compute it. So what's the progress on the backcorrection? There's old general results by Tomasiello and friends, which you should look at. This is more in the context of the pure spinor formalism. They haven't solved for the backcorrection, but they can say some things about it. And then in the recent years, people have computed the actual backcorrection order. So the people have set up a perturbation calculation, where you compute a backcorrection in a 1/n series. And what has been done is the leading backcorrection. Unfortunately, this is interesting, it was a lot of work. Unfortunately, leading backcorrection, it's kind of linearizing the problem. So it means that there's one orientifold backcorrecting, another orientifold backcorrecting, and you just put them on top of each other. So you don't see the interaction between the orientifolds. Still, it's nice. Everybody's talking about doing the second order. Nobody, I think, is doing it because it's such a heavy calculation. But it would be nice that somebody at some point could try. Okay. So there are more solutions than the ones I outlined here, which were found originally in these papers coming, on the archive around the same time. So there's a general classification within type 2A on generalized Calabi-Yau 3, which, as you can find in these papers. I want to emphasize, often this debate was about Romans mass. Oh no, you have a solution with Romans mass, there's no M-theory picture, it's bad. It's not true. You do not need to have Romans mass. Okay, there are solutions without Romans mass. This was already pointed out in this paper. And then you can actually lift them to M-theory. And then here is a remarkable thing. This is, of course, PR for myself. If you lift them to M-theory, what happens is that the F2 flux and the orientifold planes, they completely geometrize. And so there's only F4 flux and F7 flux. And so if you would understand the backcorrection of the orientifolds, that's an if, it's guaranteed that these type 2A vacua, without Romans mass, lift to Einstein manifolds, so to Freund-Rubin solutions. They would lift to Freund-Rubin solutions with scale separation. So they would go against this conjecture by Yau and Waffa and collaborators, okay? But since we do not know the all-ordered backcorrection, we cannot do this lift fully explicit. But most of the details of this lift have been found in this paper, okay? What about solutions in type 2B? It's not, the results, unfortunately, in all examples known, some cycles will be order 1 in size. So it means that you try it and you're always pushed back into the type 2A frame. Okay, there's no no-go that you cannot do it, but this is the state of affairs. And then there also exists ADS3 vacua in massive type 2A on G2 spaces with orientifold planes, okay? So that's another thing. I do not know of ADS2 vacua of this kind. All right, what about ADS-CFT? Yeah. It's the same story. So it's just a little bit more involved, but it's the same. You have a pure spinner picture. Like it's at the same level of explicitness. People have computed moduli stabilization like it's as detailed as the ADS4 vacua. Yeah. Okay, ADS-CFT. So the ADS-CFT dual of scale separation means that there are only a few low-lying single-trace scalar operators, and then there's a parametric gap. Okay, I'm just reminding you of the usual ADS-CFT formula for the mass of a scalar field, in this case, in the bulk, and the conformal dimension. So you see that this ratio, M, LADS, is exactly what appears. I say ratio because I can write this as LADS divided by LKK, in case I would look at the dual of a KK mode. So this object that we discussed for scale separation appears in that formula. Yeah. In fact, there are two parametric gaps. Any holographic CFT is known to have a parametric gap, which is the one to the string states, right? So if you want your dual, if you want your bulk to be like essentially gravity, then the string states should almost decouple, and that means in the dual CFT that these higher spin operators dual to those string states, they also decouple, meaning that there's a huge gap. Okay, so that's a known gap, which you have for all holographic CFTs. No, what scale separation does is to add yet another gap. Okay, so that's the gap, which is essentially saying there's a gap with the KK spectrum on the dual, on the bulk. Okay, so that's a weird thing already, that there are two gaps. Yeah. No, they're not related to each other. Because a holographic gap you always have, right? Yeah. So they definitely do not imply each other, because all of the vanilla ADS-CFT pairs we know don't have the second gap that I mentioned, only have the first gap, right? What's even more special, and this is funny, it's not sufficiently mentioned, is that scale-separated ADS vacua, which are suited for uplifting to the sitter, they should not have tachyons. So I mean, between the BF bound and 0. So that means that there are no relevant deformations in the dual CFT. So these are dead-end CFTs. So in the RG flow diagram, they would be the attractors. Okay? Yeah. I know. Good. Thank you. I will say what... I was too quick. What Jakob wants to say is, imagine my ADS vacuum has a tachyon, and I do an uplift, and if the uplift is sufficiently well organized, it can remove the tachyon. Yeah. There's a reason I didn't say this, but because I doubt, but you might give examples, and I'm very happy now. Yeah. So this gets close to actually understanding whether pure ADS gravity has a dual, right? Okay, I will say more about this. So what are the general beliefs here? So the two original papers you should look at are here. So a general belief is that imagine you have an arc symmetry, then you have the chiral primaries, and so they have dimensions which are protected by the arc charge, and so we need at least minimal supersymmetry and no isometries of the internal space in order to get scale separation. This belief turns out to be at least verified in all examples we know. Okay, so all examples of scale separation either have n equals 0 or n equal 1. The only thing that is, this is not a proof. So often this statement is quoted as a proof that for extended supersymmetry there is no scale separation. This is not true. Eric might say something about this later, I think, during the discussion session. So one reason that I understand, but I'm a dummy here, is that there's no proof is because there's no obvious way why you could say that a chiral primary has to be the, if you find one, that there has to be a whole tower per se. If you know that, yeah, then you know there's no scale separation in the dual CFT. Another thing which is well, it's not a belief. This is actually a true fact. I don't know why I wrote a belief here. This thing is that the crossing symmetry constraints will not tell us about, in any obvious way, about the consistency of the ADS vacuum. So you could say, oh, there's a whole bootstrap program. There's a swampland program. Maybe the two are essentially the same. Well, the problem is that to a leading order in 1 over n, you can show that any ADS Lagrangian obeys the bootstrap constraints, the crossing symmetry constraints. In higher order in 1 over n, that is not true. So there's something to be done there, but it's a tough calculation. Right, so that's why it's not obvious that you can use the bootstrap to tell us whether scale separation is possible, yes or no. An example of this is a paper by Aldai and Chester. They considered the holographic dual to pure n = 8 supergravity in ADS5 in the large ADS limit. And the model actually interestingly saturates some of the bootstrap constraints, so it's kind of in a special location. Another thing related to this is a paper by Miguel and friends, is that if you take pure supergravity theories in ADS with enough SUSY, so that there's an R symmetry, then in the large radius limit, you get a flat space quantum gravity, where you can show that the R symmetry becomes a global symmetry. And we know that that cannot happen. So that's yet another argument why you expect that with extended supersymmetry it's not going to work. But this is not a proof. Okay? Then there was a paper by Eric and Aldai in 2019. So one of the observations there is that loop diagrams in the bulk are sensitive to scale separation, since they are affected by all the KK modes. The whole tower sits in there, and such diagrams are dual to certain non-planar CFT correlators. And so the main idea is that there must exist a way there from the CFT to read off the number of large dimensions. The only thing that I do not understand, I don't think this is currently used to be able to exclude or include scale separation. It just, the main message is that there is, strictly speaking, there is a CFT calculation you can do to read off the number of large dimensions. And then there was a paper by these people, which I already mentioned before. This is a collaboration between mathematicians and physicists. So what they did is they studied a large set of holographic CFTs from branes at singularities in the Sasaki-Einstein. Well, they actually did a lot, sphere quotients and so on. And what they found in all of these examples, which we understand, is a universal upper bound for the dimension of the first non-trivial spin 2 operator. So they will probe scale separation by looking at the massive gravitons. The massive gravitons should be massive enough. And so they find that this is true. So on the mathematical analogous statement is the following pure mathematical conjecture. The diameter of an n-dimensional Einstein manifold with positive Einstein constant, n minus 1, it just means that you normalize the Einstein manifold you look at, you fix it, is bounded from below. And the first non-vanishing eigenvalue of the scalar Laplacian is bounded from above, where the bounds depend only on n. So there must be some universal number, and this will exclude scale separation. So the thing I mentioned in the beginning, whether Freund-Rubin vacua can lead to scale separation or not, that happens if I can decouple the KK scale from the curvature scale. They're saying no. But there's no proof. And as I just said, the 11D lift of these massless type 2A vacua would give concrete counterexamples to this. Okay. But the mathematical statement is a pure geometrical statement, right, about Einstein manifolds. You're asking yourself, yeah, you're asking yourself, do higher derivative couplings evade no-goes for scale separation? Sure, they should evade no-go theorems, but doesn't mean that you can find them. Yeah. 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 It rules out parametric scale separation. It means that there's no tunable number because then there would not be a fixed. Yeah. 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 I indeed very quickly assumed that if I find a KK scale, first KK particle, that the next one will be essentially at the same distance. I agree. There's no, but then there's mathematics literature which is telling you something about, yeah, there's surprising a lot of mathematics literature on this question, which is too hard for me to read, but yeah. All right. Yeah, but there should be room for questions, so I'll be very quick. Some very quick curious features about these CFT duals to type 2A vacua. So first of all, the way the central charge scales with n is very bizarre, never seen in this way. Like for the ADS4, it goes like n to the 9/2. Another observation by the group in Oxford is that if you're careful about computing the masses, which was somehow missed in this original paper on the question, then you find that the operator dimensions of all the moduli that you stabilized, they're all integers. Okay? Which is non-obvious because if you look at the formula that I gave you before, there's a square root. So you could say that the mass is maybe the combination mass times L is integer, you kind of expect. But there's no way that it picks out exactly those numbers so that the square root gives you integers. So this is not understood why that happens. Okay, that's one thing I wanted to say, but I cannot say too much about it because of a lack of time. There's a very concrete suggestion by Fien, who is here, that you might explain it if you can prove polynomial shift symmetries in the large n limit on the ADS side, but sorry, I cannot say too much anymore about this. There's also a puzzle regarding how where the would-be holographic dual would come from. If you have a bunch of large fluxes, you would think that you replace the fluxes by the branes. And of course, these ADS compactifications are more complicated than the usual Frank Rubin. But in the large n limit, you would expect that the degrees of freedom on the CFT side will be provided by the branes that you backcorrect by the branes that come from the fluxes. So if you have F4 fluxes, you would expect there to be the D4 branes, okay? And that the CFT should come from there. So you can do a calculation. This is what Fien did. And indeed, for the type 2A ones in ADS4, it reproduces everything, the scalings, and so on n of the string coupling, you name it, it's all reproduced. If you do it for the ADS3 vacua, it's much more complicated. It doesn't work anymore. We don't know why. Then I want to say something, and then I should finish, about large volume KKLT and so on. So there have been various papers on this. Well, not too many. I want to mention a paper by Joe Conlon, and then I want to mention a paper by the Harvard group. So one very interesting observation by Conlon is that there seems to be a relation, at least, between swampland constraints, which are known, which we all hold very dear, like the constraint on the decay constant of an axion, and CFT positivity bounds. Okay, so that's a general observation he made. And then what he did, he started computing anomalous dimensions and kind of extrapolated what you expect, but there's no proof. Some kind of negativity conditions. It's instead of positivity, negativity conditions on certain anomalous dimensions, which is related to the fact that two particle states in the ADS bulk should attract or not. Okay, so there's no proof, but it's kind of extrapolating from what we know from CFT. So here's an example of an anomalous dimension, and here is a parameter in the theory. Okay, I have no time to explain this. What he observed is that if you say that these things have to be negative, they have to live here. Remarkably, you check it for large volume, it's almost saturating this. So it's kind of a very interesting observation. And now I also have to rush over the Harvard result by a lack of time, but this is also a very, if true, it's an impressive statement because it starts with saying that KKLT ADS is inconsistent with holography. Okay? So what happened there is that if you use a C theorem, and you use it because you don't know how to compute the degrees of freedom in KKLT on the dual CFT, but using the C theorem, you go to the UV, you step away from the CFT, and you can do a kind of a rough counting of flux of degrees of freedom by changing the fluxes by branes. And then they find that this has to be true. Okay, so this is a topological number on the fourfold. And you see, that means that I cannot just take this very large. I cannot do scale separation. It's actually worse. They find that the species scale, which is telling you when the effective field theory should break down because there are too many light modes, is larger than this number. So if you take the radius, if you take the ratio, it means that this is smaller or equal to 1. And that means that you don't have a solution under control. So it would be great to discuss this during the discussion session because that's a huge claim if that's correct. Yeah. Exactly. So that's why I think it would be great. I'm interested to hear the criticism of people. Yeah. Yeah. That's why there's a discussion session, so it would be great to discuss this. And then hot from the press, but maybe we can leave this for the discussion session, is a result by Val, who is here and collaborators from Leuven. So maybe I can say something in the discussion session about this. But it's also, I think, is a very interesting result. And then I wanted to talk about the swampland, but there's no time for this. So let me go to the outlook. So scale-separated vacuum under control is debated from the bulk point of view, mainly because of orientifold backcorrection, or a general lack of proper 10D treatment. Like LVS and KKLT are sort of between bottom-up, top-down. The question I have is whether a holographic understanding proof of scale separation, is it equally difficult or not? There seems much evidence that supports absence of SUDI ADS scale separation with more than 4 real supercharges. That is a very interesting result that proves this as long as you accept the weak gravity conjecture. This is a result by Niccolò Cribiori and Dall'Agata. And that's very interesting. So I should have emphasized, but I had no time for the swampland. The weak gravity conjecture is not something that I think we should call a conjecture. If we do it, we should again use the word ADS-CFT conjecture, which we also don't. So we should discuss about, there's a proof for, I would say, no scale separation for extended supersymmetry. And then there's an interesting result by Val Reis and others, which I haven't been able to discuss, unfortunately. And this also excludes scale separation in D larger than 4. So D equals 4, by the way, seems to be very special from the point of view of scale separation. Thank you.
Thank you, Thomas, for that very nice review. There were many questions, but we have a little time for some more.
Can you take a little time to elaborate on the last part?
Which one? The result by Val or the?
Yeah, that holds.
So the result by Niccolò, I think, who is here. Yeah, is very interesting. Is the following: if I have extended supersymmetry, I have an R symmetry in the gravity that I'm actually gauging it. So there are vectors that correspond to the gauging of the R symmetry. And what you can show is that if you want scale separation, then the weak gravity conjecture for the R symmetry vectors is violated. The magnetic weak gravity conjecture. So to me, that's a very powerful result. And the surprising thing is that the calculation to show this is actually not too difficult. It was embedded in the whole formalism of gauge supergravity. It's just that nobody observed this before they did. So by the way, this should be interesting to reformulate that in dual CFT language. You should be able to do it. It's something we wanted to do when we haven't done it yet. Yeah, that's what I mean. One should formulate this in the weak gravity in dual CFT, which is related. Well, Miguel, you worked on this.
I was going to say that the dual CFT statement is just the statement that there's a BPS bound they are charged, the dimensions are controlled, they
No,
are
but
charged.
as I said, that's not enough.
Yeah, you need to say that they are populated, right?
Yeah.
You say that with gravity does they are populated.
Yeah.
Like a strong version of with gravity is almost assuming that there's no separation, right? Because it tells you there's the gravity charge 1, 2, 3. The question is if you have mild version of with gravity, so this is one guy of charge 1 million, or
Good.
yes.
Very good. Yeah. Yeah. True. Yeah.
Could you say more about this open strength theoretical reflections? I saw you had one page where this kind of just step that you just skipped or whatever.
On the swampland?
Yeah.
Okay, very quickly then. So the way Pauti, Luce and Waffa arrived at the what we call the ADS distance conjecture is by calculating distances between ADS vacua, and then you apply the distance conjecture. And so the way they computed distances was distances in metric space. What you can also do is instead of you say, I don't feel comfortable of computing distances in metric space, I want to go back to the original idea of the distance conjecture and compute distances in scalar field space. You can do it if you integrate in open stream modes. And then you find that all the front ring vacua, but also the scale separated vacua, nicely obey the distance conjecture. So they exactly have this exponential behavior and so on. So in that sense, you cannot use a distance conjecture to rule out scale separation, it seems.
So the 11 dB ability you mentioned is scale separated one. Do they have non-linear warping there?
No, the warping exactly cancels out, at least at a leading order in 1 over n. It could be appear at 1 over n squared. The intuition is that, you know, 6 plane, which causes the warping, geometrizes. So in the M-theory uplift, the dilaton dependence exactly cancels the warping dependence.
Okay, I'm sure there are more questions, but we have a discussion, so let's thank Thomas again.